Okay, right. Well, I'm going to talk through some of the development work that Starlab has sponsored on the DomB project. Um, but this is going to be a presentation on things that we've built so far, and there's a subsequent design session, hopefully scheduled for tomorrow, where we can open it up to more of the discussion about the things that doing this work has raised, and possible preferences on future direction, so that we can aim for integrating this into Zen. So, quick overview of what the DomB project is about. That it's about restructuring the way that the Zen hypervisor launches its initial set of domains. Currently, classically, Zen boots a single domain, domain 0, highly privileged, typically responsible for managing your hardware. And we're proposing to modify this with a proposal to introduce a probably small, short-lived boot domain that then takes on some responsibility for configuring other domains that are also constructed by the hypervisor during system boot, um, so that you can launch multiple domains as part of boot, but also have the opportunity to um, have control over what permissions get assigned to them, how they are configured, measure them in support of the DRTM architecture that is supported by OpenXT and TrenchBoot. So the ability to launch multiple domains at host boot actually has multiple use cases, um, even beyond the security focus that brought this about. The thing that drove Starlab's interest in this was feedback from customers that they are concerned about the level of privilege that is typically assigned to a DOM0. They prefer not to have that, and DomB is a way that you can launch a system without a DOM0. Um, but it's also the launch of multiple domains has already seen appeal in the ARM branch of Zen, um, where the DOM0less work that Stefano implemented already enables launch of multiple domains, but the DomB proposal restructures it slightly to provide these additional measurement and granular control capabilities. So the reason for talking about DomB in this context, and seeking out this feedback in the design sessions, is to ensure that we build this architecture that is flexible, that is useful, and so it becomes widely deployed, um, and consequently is well tested, well maintained, and well understood by the Zen community. Just to run through some of the use cases for the DomB architecture, deprivileging DOM0 was the original motivator for this particular piece of work. We're instead of starting a single highly privileged domain, we can look at starting several individually less privileged domains that take on some of the roles that would classically go to DOM0. Another example is the VTPM architecture, where you want to be able to start the VTPM components without having them within launched and subject to DOM0's control. It's a better fit with the disaggregated DomB architecture. So system partitioning, you're able to statically assign resources to domains. It's a way of using a hypervisor that is typically simpler than the general purpose cloud virtualization or server virtualization in case where things are VMs come and go. If you just want to do static partitioning, something like DomB can be very useful for that. The low latency boot and reboot is also a use case. I think that Stefano's work the DOM zeroless work was motivated by the ability to bring guest VMs up very, very quickly, not have to wait for DOM0 to initialize the tool stack to become available before you start getting your other VMs up and running. And then the final use case is so this isolated multiplexing of singular system resources. A TPM is one example of that. By having a domain come up early at host boot and mediate access to that resource, you can have good control to ensure that the multiple clients for it can each do so without treading on one another. So some of the objectives we took into account when designing DomB, an important one was compatibility with existing Zen behavior. There's many systems out there that have a DOM0. We mustn't break the ability to have that configuration if that's what you need. We'd like to have a default build of Zen in the binary, support booting either into a classic DOM0 or into the DomB. You should be able to kconfig either one of those in or out of your hypervisor, but they should be able to coexist with automatic selection depending on the boot configuration for your particular host, preferably with no modification needed to the bootloader. We're seeking to make it pretty intuitive to configure using familiar tools, technologies, or configuration. One of the pieces of feedback we got on early on was that predictable, accessible failure behavior was going to be important. So if you screw something up in the config, you can get to a console. I think this is born of people having real world experience of supporting Zen in production. And then I guess the other requirement that's pretty important here was we needed to be able to boot an x86 Zen environment with no need for a DOM0. That was one of our exit criteria for demonstrating the concept work was viable. In building it, we have a preference for supporting PVH for the boot domain and also the other initial domains that are launched when Zen comes up. The motivation for this is just to avoid the pitfalls of legacy PV interface. It also means that PVH rather than HVM, you don't need QEMU. That would just add complexity since starting a device emulator has a more involved construction sequence. And another benefit of aiming for PVH is it aligns x86 with the Zen on ARM architecture where all VMs are PVH style. So related work prior to this project getting underway is the first would be the DOM zeroless work and then Zen on ARM. This is where a set of domains are launched at host boot, but they're done in parallel from a configuration in the device tree, and there's not the opportunity for a single domain to interpose, perform validation measurements that we're looking for DomB. So in this sense, DomB is sort of a step away from the DOM zeroless very fast Zen initiate everything that it gets its hands on. This is more of a controlled boot sequence where a single domain gets to inspect the incoming configuration, look, has the opportunity to interact with the domains that the hypervisor has constructed before any of them ever get scheduled. Another piece of pre-existing work was the late hardware domain. This is where I think it's x86 only. I may be wrong on that, but I think it is. It's where you boot a system with a DOM0, but then a subsequent domain is launched that is identified as the hardware domain by a Zen boot command line parameter, and DOM0's hardware management capabilities are then transitioned to this newly launched domain, and your DOM0 is deprivileged at that point. It's a useful logic for building some of the DomB stuff, but the hope is that DomB, when complete, will enable retirement of the late hardware domain feature, and that it will subsume that capability. The next piece of work to mention pre-existing is the support for booting a PVH DOM0. There's quite a bit of very useful domain construction logic within Zen for building that PVH DOM0. It then assigns it the classic DOM0 privileges, which is not the path that DomB takes, but it's a useful set of code for being able to construct PVH domains within the hypervisor. And the DomB work, leveraged quite a bit of that. The structure of booting when you are operating in the DomB mode is the first multi-boot module that the hypervisor receives. Traditionally, that would be the DOM0 kernel, and the DomB proposal replaces this with we call it a launch control module, and this is metadata about the domains that are to be launched and the other multi-boot modules that are provided by the bootloader. And it's this detection of the presence of a launch control module rather than a DOM0 kernel that toggles the DOM0 versus DomB boot method. So as part of this work, we've produced a tool that can produce a launch control module binary. It takes JSON config as input, produces this binary that then goes to the hypervisor. So the next component is the boot domain. So you'll provide a kernel and optionally a RAM disk, and this is the single domain that is unpaused by the hypervisor at boot. It effectively replaces DOM0. It does not have the capabilities, the privilege capabilities of DOM0. And then the hypervisor will build additional initial domains as described in the launch control module, and with kernels and RAM disks that are provided as multi-boot modules. None of these are unpaused by the hypervisor. It's when the boot domain gets to run, it has the option to interrogate the hypervisor and decide which, if any, or all of the initial domains that it will unpause. And so the remaining components of the work are Zen modifications to implement this, and some changes to the Zen tools to remove places where domain 0 is assumed. To the launch control module, it is a binary module. It conveys basic configuration data for the hypervisor to use to build the initial domains. It also conveys extended domain configuration data for the boot domain to apply to the other initial domains. There's this division of the domain configuration between that which is acted upon by the hypervisor and the remainder, which can be much more verbose, more detailed, which is acted upon by the boot domain. And the boot domain can be custom. The hypervisor implementation is common, shared between all users of Zen, But the implementation of the boot domain is entirely up to what you choose to deploy. You can provide your own kernel, your own RAM disk, and so this extended domain configuration data is free format, and you can write whatever logic you want to go into that boot domain to apply that configuration data according to what it is you actually want to boot. So a critical requirement is that the basic domain config data is simple to parse and navigate, and so we use fixed size elements to enable the hypervisor to easily traverse it. And a future goal is for this launch control module to actually be dynamically instantiated by the bootloader itself, so that you don't actually need to precompile this launch control module based on what you want to boot, but the bootloader can generate it based on the bootloader config. So this is example JSON input to the tool that generates the launch control module, and this describes the data that goes into it. And this is a simple config where at the top it's describing 3 multi-boot modules. It's providing a type for each of them. There's 2 kernels and a RAM disk, and there are 2 domains being constructed. The first is the boot domain, and you can see the metadata associated with the boot domain, amount of memory, the flags that determine the capabilities of it, resources assigned to it for the boot domain. And then there's a second domain which you can see is described as a hypriv with a hypriv config. This is basically a way of constructing a classic DOM0. When this is encountered by Zen, it will go, okay, I'm going to use the existing classic DOM0 path, and this will should give us maximum compatibility with all of the logic that has previously been used to build a DOM0. And that's it. So in this case, you'll have a boot domain. It'll launch the boot domain. It'll construct you a DOM0, but it won't unpause it. It'll be up to the boot domain that you actually launch to unpause the DOM0, and presumably the boot domain's work is done at that point, and it will exit. This config is a somewhat more involved, but perhaps more realistic for DomB use case, where we've got 4 domains. We've got, if you look at the modules in the top left, you've got 5 multi-boot modules, 4 domain kernels, and a RAM disk. And sort of in the top left, bottom left, top right, bottom right, you've got 4 different domains. And in this case, there's a boot domain, there's a hardware domain, which is indicated by the hardware flag being true in the permissions logic, and then we've got 2 DOMUs on the right hand side, one just a kernel, and the second one with a kernel and a RAM disk. And to note, in the DOMU configurations, you've got both a basic config where you've got fields that are interpreted by the hypervisor when it's building the domains, and you've got an extended config which is effectively free format text, and the aim is for this to get passed up into the boot domain, where there's basically an agreement between the thing that you pass in to generate the launch control module and the logic you have in the boot domain as to what you do with that data. It's your boot domain to use it to configure the domains correctly. So in that slide previous with the rather large amounts of JSON stuff, we've got no domain 0. There's no privileged domain present, and if you boot this way, unless you've written a custom XSM Flask policy to allow you to do so, you can't actually start anything with the DOM0 privilege. Your domains will run, and when the hardware domain exits, that's when your host will reboot. We've got a PV hardware domain. In the prototype we built, we went with using PV for hardware domain just because the majority of Zen deployments use a PV DOM0, and we wanted to avoid any excitement with bugs from PVH hardware domain. PVH is, at least for privileged domain, is still experimental. And in the config file, we've got two PVH DOMUs. As I just described, it's a free format config in the extended config, and then the XSM Flask SIDs, which are associated with each of these domains as one of the items in the basic config, can determine the granular permissions of each domain. So that what I showed previously was the JSON input to the launch control module tool. The binary output is dictated by some simple C structs. I'm not going to walk through these in detail, but the aim is to show these are simple structures for the hypervisor to be able to parse in the binary data and to work with to reduce the opportunity for error in working with the launch control module. And again, with these two slides, you have most of the file format for the launch control module defined. Simple values for flags. Okay, so the launch path in Zen. First of all, Zen will detect whether there is an LCM as the first multi-boot module or not by inspecting, looking for a magic well-known value at a fixed location in the file, which will toggle between DomB and classic DOM0. And then it will parse the LCM just to validate it, to make sure some basic constraints are satisfied so that it can be navigated safely. And it'll look to see whether you've got any boot domain, hardware domain, and a high privilege domain. Board flags for those three things. It will classify the multi-boot modules. So on x86 at the moment, there's 4 different uses Zen has: the kernel, RAM disk, microcode, and the Flask policy file. It will then build separate module maps, and then when each of those file types is needed, it will go to the right thing and make sure it's using a multi-boot module of the right type. It then proceeds through to the point where Zen constructs and then Zen creates domains based on the information in the basic config of each domain. So the sequence is that the boot domain is created first. Any highly privileged domain is then created next, if there is one, and it's processed the same way as classic DOM0, and then the domain construction logic is executed, which does the more involved P2M table assembly, assignment of a vCPU, the remaining bits before you can actually launch the domain. And then it'll drop into a loop after it's done the boot domain, the highly privileged domain. It will drop into a loop cycling through domain creation and construction for any other initial domains described. A single domain gets unpaused. The logic is pretty simple. If there's a boot domain, that's the one. If not, if there's a highly privileged domain, it'll unpause that. And if not, if there's a hardware domain, that's the one that gets unpaused. And if you haven't got any of those, then your LCM won't validate and you've given it an invalid config. And as part of this work, the initial work, we built a sample boot domain. I worked with Daniel Smith at Apis Solutions on building this, and he implemented a Linux kernel module that just loops unpausing domains by incrementing DOM-ID, which allows the boot domain to unpause the other initial domains, and then the boot domain connects it and leave the other domains running. In the boot domain that we built, it's currently single vCPU, always runs on the BSP. It was simpler to implement and it's actually probably pretty reasonable constraint for a boot domain. At the moment, we've implemented PVH only. Should implement PV to be able to provide a fallback for at least some better behavior on a misconfigured machine. The E820 map generation for the boot domain is a little different than the existing logic for building a PVH DOM0. PVH DOM0 will pass through a sort of a modified variant of the host E820 map for the boot domain because it doesn't have any hardware access. We aim to have the same configuration VM environment across any deployment. So we put together a fixed, simple E820 map. In the config we built, we require hardware-assisted paging just to set those flags. No shadow page tables for the boot domain. You shouldn't need them. Modern hardware should provide you with HAP. And then no custom processing of the kernel command line. DOM0 has some logic where Zen options can be propagated to DOM0, but since the boot domain is not a hardware domain, we don't need that. Okay, and then looping through building the PVH initial domains, the nice side effect of this is that the tool stack is removed from the TCB of those domains at the point where they're constructed. So you don't need any logic from libxl, libxc, zappy, HVM loader. When writing the logic to build these PVH initial domains, a lot of the existing PVH DOM0 construction logic was borrowed. There are some things that were encountered on the way. It turns out that calculating the exact amount of memory to assign to a domain is rather more involved than you would think. There is a function that does it for DOM0, so as part of the prototyping, we've borrowed that, but it needs to be gone back, revisited, and done properly. There's logic for building the P2M table, and then there's ACPI table generation. So that is also done custom for both the boot domain and the PVH initial domains. And that's a thing that probably we ought to talk about in the next design session. Yeah, and then the PVH initial domains borrow the E820 map generated from the boot domain. That needs revisiting if there's hardware to be assigned. And so we've built a proof of concept. It boots. You can give it different configurations defined by the LCM. It can launch a system as described in the earlier config file, where there is no DOM0. There is a hardware domain and a couple of DOM-Us. Yeah, basically does what we set out to do there. And you can see the kernel launch messages of each of the domains that are started on the Zen console. The caveat is that PV devices are not connected since the back-end ZenStore data and toolstack handshake has not been done. You don't have a domain with the is privileged capability. You're not running a standard tool stack. You can run ZenStore D. That's launched by setting the bit for the domain in the LCM. We currently set that on the hardware domain, and so ZenStore D can be started when it's told the right domain ID. ZenStore LS works. There are some other modifications you need to remove assumptions of DOM0 in the Zen tools. And yeah, at this point we've deferred making the secondary configuration of domains by the boot domain actually happen. come back to that. So a set of issues noted during building this. Basically, it was quite educational to go through the code and actually make this work. There's a number of challenges that are not necessarily there at first glance, but are necessary to resolve in order to build this to be a production capability. So the guest memory calculation is a little complex. There's internal memory resources needed to support an x86 guest. For Zen's own needs, you can't just give all of the memory to the guest. E820 map construction may need to differ when physical hardware is assigned. The ACPI table construction that's needed in order to start a PDH guest, that could be quite an involved piece of logic, especially if there's what very likely to be multiple vCPUs assigned to the domain, possibly also with additional hardware. It's an open question as to whether we should be performing this work in the boot domain, the building of these tables, to deprivilege that logic and enable flexibility in the implementation of it. We've not yet settled on a method for exposing the launch control module to the boot domain. I'd also like to expose the other domain materials from the multi-boot modules or the initially constructed domains, so that measurements can be made on those domains by the boot domain before the other initial domains are unpaused. In the prototype we built, we stuck with single vCPU per guest. Secondary vCPU bring up comes with additional complications that should be resolved. Configuration of those vCPUs is probably appropriate to do by the boot domain, exercising invoking the hypervisor to do it. We need to talk through how we should do that. Guest kernel decompression turned out to be rather unpleasant. The kernel changes size when you do this, which makes sense, that's why it's compressed. But you need to do a headroom calculation on each kernel you're provided with, and it affects the sizing of page tables, an input into the relocation logic. It's questionable whether that needs to be done within the hypervisor. I don't know. In order to make the thing work, we had to make some minor modifications to hardware domain permissions. Things that are normally available to DOM0 because it's privileged were not available to that hardware domain, even though it had the I/O capabilities, but it didn't have the standard is priv. And there's just a few operations that need to be whitelisted for the hardware domain that touched upon when getting it stood up. The console, the rudimentary plan was to just assign the console automatically to the single domain that Zen unpauses, which could be DomB, could be DOM0, could be the hardware domain. And when it exits, you transfer it to the hardware domain. Like to implement validation of the multi-boot modules so that the launch control module can provide a hash so that you can check that you have actually been handed the right data as your multi-boot module expected. That's possibly a bit of an expensive op, particularly if you're using this boot method because you want a low latency start of your VMs. The atomic handoff is about it would be nice to have the property where the boot domain never executes concurrently with other initial domains if you want to configure it that way. So it's a question of how best to do that. We could leverage something like multi-call so that the boot domain shutdown is in the same hypercall as general purpose unpause of the domains. But it's not clear that multi-call is the right thing to use. Some advice from people familiar with that would be helpful. And then there's decisions to be made about error handling if your hardware domain doesn't unpause, or if your boot domain exits before you've got a hardware domain. What do you do? There's some work to do to make the tool stack aware of initial domains. So when you do boot up into a control domain, there may be more things running than your tool stack is expecting, and it would be nice to be able to enable use of PV devices in your initial domains, or enable construction of HVM initial domains, so the stitching together of multiple domains if you're using stub domains, for example. Okay, so I don't actually know how I'm doing on time. Where are we at?
You have 6 minutes left.
Thanks, Andy. So yes, what next? So please come to the DomB design session tomorrow. I've basically plowed through this as quickly as I could with as much of an information dump about what has been built so far. But I'm interested in getting people's feedback on this, on what kind of use cases they can see for it and what they'd like, what the requirements for that would be, because we do want to get this built for inclusion in Zen, and then hopefully widely used, made available. Somewhat related to the original requirements that drove building this for Starlab is we'd like to be able to use PCI pass-through with PVH domains. So figuring out how to do device pass-through to the initial domains and making that work with PVH is of interest. Also interested in looking at aligning this with the Zen on ARM code base. I don't really want to make this x86 specific, so I've been doing a little work recently with the Zen on the Raspberry Pi 4. So that's probably the first place I'll start if I get to look at the reconciling this body of code with the ARM code. And then the last thing is there's a pointer here to the RFC that Daniel and I posted to ZenDevel a couple of months ago. Should be familiar if you've just listened to me talk for the last half hour, but yeah. So thanks to Starlab for sponsoring the work, Daniel for helping me with the design and implementation. Thanks to the Zen community, Rich, OpenXT, the open source Zen team at Citrix, including Lars, who's sadly missed and was very helpful with arranging for meetings with the open source team and Daniel, Rich, and I on a visit late last year. Thanks Jan for reviewing the patch submission, Roger for implementing all the PVH DOM0 stuff, and Daniel the graph, the late hardware domain, and Stefano for the discussions about DOM0less. That's the end of my presentation. So any questions?
You have some questions in the chat already.
Okay, great. Okay, so memory use is a swamp. Yes, thanks, George. Might take us a bit to work on that one. Okay, wouldn't it be more natural to use ZenStore stub domain instead of ZenStore D in some other domain? Yes, totally happy to do that. This was getting the ZenStore D up and running was actually done really quite late in the sprint. We're happy to see it running outside of a DOM0, but yes, creating a ZenStore D stub domain is definitely definitely an interesting thing to do. I think that would be a good fit for OpenXT and possibly Cubes, other systems that want disaggregation. Okay, thanks for the feedback.
So one thing is, this is Stefano. So we are working with other companies and proprietary hypervisors to come up with standards, as in community standard, to do configuration of static hypervisors. And since this would fit very well. By me, I mean configuration of multiple VMs to be started at boot, and that whether it's Zen or WindRiver or another hypervisor, it should work kind of regardless. It's based on device tree, and it's under the system device tree umbrella at the moment as a name. But we already started talking about an equivalent in YAML format, which might better fit if you don't want to use device tree. Anyway, I think you should be maybe more involved, and maybe it looks like it's a good fit for the DomB configuration.
Okay, thanks. I'll be interested to take a look.
Yeah, I would add the comment that we were looking at device tree, but we had a timeline to get in, so we wanted to implement something that represented exactly what we needed to, and then we could look later at readapting this to device tree or any other efforts that might be going on.
Bertrand Marquis from ARM. We are working at a concept named Safety Island on ARM, which would have lots of commonalities with the DomB, and I kind of think that we should be able to come out with some standard interfaces and features, especially for Xen Store, because we have exactly the same problematics. I will show it briefly in my presentation tomorrow, but looking forward to discuss this with you in the design session, definitely.
Great.
I think it's possibly worth saying I appreciate that we're adding compatibility for all operating modes, particularly when you have a DomB that is attempting to measure the kernels from the other booted domains. What you will find is that a PV DomB will perform much better than a PVH DomB, simply because of the different mechanics of how you perform foreign memory maps. So an unprivileged PV domain isn't really more or less security friendly than an unprivileged PVH. I think it would be useful to support both and to come up with some actual real measurements, because when you switch to having a microkernel for DomB to get it completed as fast as possible, I suspect there will be a big difference between the two, and it will be in favor of PVA, in favor of PV rather than PVH.
That's interesting. Okay, yeah, and particularly given that the DomB boot domain is not typically going to be running concurrently, or at least not doing much concurrently with the domains. The idea is that it does bulk of its work before it ever unpauses them. It seems like your exposure to risk with running a PV domain is somewhat reduced.
Yeah, and bear in mind that the microkernel design removes all the bits of PV guests that are traditionally slow and complicated anyway.
Well, we're over time, so I think we've got another design session. I think it's pinned to be tomorrow. So anyway, we've got another design session we finished stuff with. Cool.
Thanks,
Chris.
Okay.
Thank you.